Laser-engineered net shaping is an additive manufacturing technology developed for fabricating metal parts directly from a computer-aided design solid model by using a metal powder injected into a molten pool created by a focused, high-powered laser beam. Slicing software will create paths for the lens system to follow when producing. These paths are instructions for geometry, and they contain information what speed to print at for various points, and what layer thicknesses to adopt. More advanced slicing programs also take into account geometric dimensioning and tolerancing. A high-power laser is used to melt metal powder supplied coaxially to the focus of the laser beam through a deposition head. Neodymium-doped yttrium aluminium garnet lasers are optically pumped using a flash tube or laser diodes. Those lasers typically emit light with a wavelength of 1064 nanometers in the infrared. Hence the visible light emitted by the process is not the laser, but the metal glowing from the heat. The laser beam typically travels through the center of the head and is focused to a small spot by one or more lenses. Metal powders are delivered and distributed around the circumference of the head, either by gravity or by using a pressurized carrier gas. An inert shroud gas is often used to shield the melt pool from the atmospheric oxygen, for better control of properties, and to promote layer-to-layer adhesion by providing better surface wetting.
Due to the heavy laser construction, the XY table is moved in raster fashion to fabricate each layer of the object. The head is moved up vertically after each layer is completed.
The lens technology is applied to various industrial use cases. Using the advantages of the process, a thin titanium edge part can be repaired using additive manufacturing. The achieved surface finish reaches up to 12 micrometers Ra. The good mechanical properties of the obtained part can furthermore fill up and applicate materials to a turning hub. The XY platform is not needed, neither is a motion in Z direction. The deposition rate ranges around half a kilogram per hour. As mentioned beforehand, it is possible to create thin wall structures. Lens can process gradient material to enhance the compatibility with stainless steel fittings of any other products. For restoring inner diameters, inside blind holes, and non-line of sight areas, the lens system is also the process of choice. Especially geometrically shaped head can reach those complicated spots.
As to be seen in the infrared thermography of the heat affected zone, the temperature in the focus point of the laser reaches up to 1900 degrees centigrade. This can result in a deformation of the crystalline structure of the metal, depending on the used powder material. Due to the poor surface roughness of 12 to 25 micrometers Ra, a surface finish is needed for the manufactured parts. More than one type of powder that is directly dispensed during production can be used at the same time, allowing the production of parts with chemical composition gradients. It is thus possible to work with reactive metals such as titanium and zirconium. The lens process can be used to produce dense shapes, which makes it also possible to manufacture properly sealed parts, such as tubes and valves. Since no support material is needed to rapidly manufacture via laser-engineered net shaping, it is even possible to produce parts that include inner hollow spaces, such as cooling channels. The mechanical properties of parts manufactured with laser-engineered net shaping are very good in terms of yield point and stress resistance compared to other rapid prototyping processes.